Okay, so very briefly rehash what I just talked about. Projectile motion. So if you've ever seen like the ads for Vegas, what happens in the X stays in the X, what happens in the Y stays in the Y, like what happens in Vegas stays in Vegas. So here's the deal. Instead of just having vertical motion, you have vertical motion with horizontal motion. But literally, if you remember this, what happens in the X stays in the X. What happens in the Y stays in the Y. If you remember that, projectile motion really isn't that difficult. There's actually no new equations to learn. We just have to like repackage the equations that we have. So with projectile motion, there's two broad types of projectile motion. One is where something goes flying off of a cliff like this, what I call a lemming problem. And then you're going to have like a golf ball problem where you hit it and it goes up and it comes back down. Does anybody know what lemmings, according to the legend, what lemmings are known for? Yes.
They don't follow each other off a cliff.
Beautiful, okay? According to the legend, lemmings follow each other off the cliff. So if someone says, hey, don't be a lemming, don't follow the crowd and jump off of a cliff, okay? Literally, that's what that means. So here's the story of the lemming problem, and this is all we're going to talk about today. The main thing about lemming problems is that this thing is going to take off with some horizontal velocity. But it will have no vertical velocity, okay? So what that means is if I drop it, or if I just throw it horizontally, doesn't make any difference. If it's launched horizontally, drop, doesn't make any difference.
No.
The only velocity it's going to have initially is in the horizontal. It will have no initial vertical velocity. Obviously, though, with the golf problem, you're going to have two things. You're going to have Vx, and you're going to have Vy. We'll deal with that tomorrow. Don't worry about that. Golf problems will hit tomorrow. No pun intended. Only thing we're going to deal with is lemming problems today. So, here's the key assumption that we're going to make about Vx. We're going to assume that your Vx stays constant. So, if I shoot like a cannonball out, and that Vx is, say, 10 meters per second, then what we're going to assume is that that flies through the air, that Vx is not going to change. Now, in reality, especially if you've ever played outdoor sports in Kansas, and there's a wind, you know that is a bold-faced lie. Okay, it is an absolute non-reality based assumption. Because if you've ever like kicked something with the wind, like you kick that thing maybe a third again as far as you normally would, or be able to hit it a third again. Okay? But if you're going into the wind, guess what? It's a train wreck because it's just going to knock that thing down. So, but here's the problem with that. If you begin to take wind into account, then you have to take a whole bunch of different things into account. The mass of the ball, the drag coefficient of the surface, the wind direction, is it with you, is it against you, and it gets real complicated real fast. That's the reality, but it just muddles it up so much that we just don't worry about it. So what happens in the X remains constant in the X. So whatever Vx you have stays the same. In reality, that's not true, but we're just going to make it that way. Trust me, be thankful, because otherwise it turns real ugly real fast. Scooter, what's the one equation you can use if you have constant velocity?
Velocity, or what?
There's one equation you can use when you have constant velocity. Distance equals,
Something over time.
how about velocity times time?
Oh, sure.
Yeah, that too?
That too.
Okay, or that.
I guess that one works.
Okay, so in terms of horizontal motion, we're going to make this look fancy. Okay, it's like, ooh, fancy. We're going to call that range equals Vx time. So when you talk about range, what you're talking about is the horizontal distance that the ball travels, okay? Or the lemming or whatever it is. So range is your horizontal distance. That's just your distance, that's all, don't flip out. Vx, again, what happens in the x stays in the x. This is how long it's in the air, that's it. So what that means, Luke, if I'm going to draw a velocity time graph for the horizontal motion, what's that going to look like? Your Vx is constant. How are you going to draw a constant velocity on a velocity time graph? Yeah, it's just a horizontal line. Now, Connor S., if there's a horizontal line on a velocity time graph, what's the value of your acceleration? Do not make this difficult.
0.
0.
Okay, I said 0. You're scaring me.
Oh, I didn't hear you.
Oh yeah, no. Okay.
I heard it.
I prematurely answered them.
Okay. Now, what are the two ways? There are two situations where an object can have a constant velocity. Two different ways. Deacon, what's one of them?
If there's a net force of 0.
Created by what?
By all the forces adding up to 0.
Yeah. So if I take this physics book and I push it along like this, I can make all the forces add up equal to 0. My applied force is balancing out my frictional force, the gravitational force is balancing out my normal force. Everything adds up to equal to 0. As soon as I stop pushing it, what does it begin to do?
Accelerate.
Because now there's an imbalanced force, right? Cool. So that's option number 1. All the forces add up to equal to 0. Chuck, what's the other option that I could have constant velocity?
And the object's at rest?
Nope. It's moving. I have to have a non-zero Vx. So being at rest is not an option. Think about if you're in deep space. Chuck, if you're in deep space, what forces are acting on the object?
None.
So the other option is either all the forces add up to equal to 0 or
No forces.
there's no forces at all. Okay? That's the only way that you can have constant velocity. Either the forces balance out or there's just no forces acting on it and therefore the inertia keeps it moving at a constant speed. That's it. There are only two options. So if I take this and, you ready? So I'm going to throw this, okay? Now when I throw it, as soon as it leaves my hand, what forces are acting, as soon as it leaves my hand, what forces are acting in the horizontal direction? Dylan.
Direction of motion.
Connor S.
None.
There aren't any. It's left by hands. What's the only force? There are no forces acting in the x direction. Okay? So without a force in the x direction, what's your acceleration? Connor S.
0.
0. Okay? That's why it maintains that constant horizontal velocity. Now, throw it back.
Pause.
My bad.
So, now, when I throw it, is it going to accelerate in the vertical direction?
Yes.
Yes. Why?
Gravity.
Gravity. I have an unbalanced vertical force, but I don't have any forces acting in the x direction. That's why I say, hey, pirate.
What?
Arr. Throw this and I have to go right down that tube.
Do it.
I'll catch it.
Huh?
It won't hurt that much.
Okay. So, this is why I say what happens in the x stays in the x. What happens in the y stays in the y. All right. Now, I want you to pretend that none of this exists.
None of what exists.
You're getting ready for the acceleration test. And I'm going to drop Gary the golf ball from a height of 2 meters. I want to know how long Gary is in the air, and I want to know the velocity when Gary lands. Okay? You don't know anything. We have not studied forces. Nothing. You're just getting ready for the acceleration test. That's it. So, Mr. Hanna,
Huh?
I know how far it falls. What else do I know?
Acceleration.
Okay? I know G is going to be 9.8 meters per second squared. What else do I know? I'm going to drop it. What's my initial velocity?
0.
Vy is going to equal 0.
Right.
So, Mr. Hanna, what equation relates distance, time, initial velocity, and acceleration?
To find the time,
Yep.
we need that. No, we need the distance equals f at squared plus v dot time.
Beautiful. I'm going to drop it. Mr. Hanna, what's my initial velocity?
It's gonna be 0 when you drop it, so that cancels out.
So, Mr. Hanna, I need this equation solved for time. And I hate fractions.
You hate fractions, so do I.
I mean, really, who likes them?
Time or t equals the radical 2d over a.
Beautiful. Okay? Cool.
Why not?
Why not?
Yes.
So, somebody take
There you go.
2 times 2 meters divided by 9.8 meters per second squared. Technically, those are negatives, but for the sake of argument and time, what do you get?
12.7.
Something like 12.7.
12.7?
Who? What'd you say?
Me?
Yeah.
I said somewhere around 0.7. I don't know.
Oh yeah, somewhere around 0.7.
About 0.63.
Yeah.
0.6.
4.
0.64.
0.64.
Okay, 0.638.
Yeah, I mean,
Okay.
I was gonna say
0.64 seconds. Which seems about reasonable, right?
Yeah.
0.64.
Yeah, I was gonna say
Okay.
that.
Now, Mr. Hanna, what would happen to that time? That was me dropping the golf ball.
Yeah.
What would happen to that time if I dropped Hank?
It would stay the same because gravity is not changing.
The gravitational acceleration isn't changing.
Yeah.
So why did, if you look at the entire test on acceleration, the ball off the building problem, you know, where you threw the ball up, came back down, all that, why did I never give you the mass of the ball?
Because it doesn't matter.
Doesn't matter. On every projectile motion problem, am I ever going to give you the mass of the baseball, the golf ball, whatever it is?
Hopefully not.
No. You know why?
It doesn't matter.
Doesn't matter. Does it affect force? Yes. Does it affect your acceleration? No. Okay. So, I need to figure out how fast it's going, but I don't want to use that time in case I screwed up that calculation. So, Scooter, what can I use that doesn't involve time?
That equation.
So I can go v squared equals v naught squared plus 2ax. Initial velocity is 0. So somebody take 2 times g times 2 meters, and then the square root of that. It's 6 something.
Okay, 6.26.
6.26
I got like 6.26, something like that.
meters per second.
Yeah.
Beautiful. Okay?
Didn't matter.
Cool. Now, here's the next thing. I'm going to go to a cliff 2 meters tall. In one situation, I'm going to launch a ball horizontally at 4 meters per second. The exact same time, I'm going to drop a ball straight down. So, Mr. Etheridge, which ball is going to hit the ground first?
The one that's going straight down,
Why?
because that's a really good question.
It is a really good question.
Because it was right.
Wait, are they gonna hit at the same time?
That's what I asked you.
I know, that's what I'm thinking through this, okay?
That's the whole point of life.
I think they're gonna hit at the same time,
Why?
because you release both of them from the same,
Height.
height is, right?
Yep.
Yeah, and gravity.
But one's shot out horizontally.
Yeah, and you said that x stays x and y stays y. So the only thing acting y is gravitational acceleration. So they'll hit at the same time.
Okay? So, Andrew, you're gonna have to spin that around back over here. Okay. So what I've got here, just for this lab, it's a little spring, and it's back here like this. The back of the plunger sticks out, and I can take one of these marbles and hook that on the end, so when I launch it, that falls straight down.
So anticlimactic right there. I was thinking we're getting like a cannon or something.
Well, but at the same time, I'm gonna take another one that's going to shoot it out like that.
Whoa.
Okay?
I'm trying to shoot someone across the classroom.
Okay. So, here's what I've got. So, I'm just gonna here, and that action.
Oh, I see the vision. I know where you're going here. Yep,
Okay?
I knew it. Let's see if he's right or not.
I'm definitely.
I know.
Okay. So, I got to use line. But, so, that side should fall straight down. This side's going to get shot out. 3, 2, 1.
Look! Look at you!
Did they hit at the same time?
It looked like it.
They did.
Look at you, look.
Why?
Okay, play it.
Because x stays in the x and y stays in the y.
And what happens in the Y?
The gravity.
Yes. Now, here's the other thing, and this is gonna be important as we get into more.
Acts of violence are being committed, apparently.
What?
Is
Oh, that's what you
it still recording?
Yeah.
Okay, sorry about that. So here's the story. Mr. Etheridge,
What?
here's the story. You ready? Okay. So when that got launched out horizontally, were there any forces acting in the X direction?
Yes. Like when it got launched. But
No, after it got launched.
Oh, no.
No. So when that ball fell, it went on a parabolic path like this. Okay? So as it fell, your Vx stayed the same. Okay? So when you look at what's a factor and what's not a factor, when you looked at the Hanna equation, assuming that it was launched on a horizontal plane, assuming it was launched in a horizontal plane, what are the only two things that determine how long it took to hit the ground?
Gravity.
The acceleration due to gravity and what?
Distance.
Distance. That's it.
Right.
It's how far it fell and the gravitational field. That's it. That's it. Could you plug Vx into that equation for time? If you try.
Yeah.
Where?
I'm just saying yeah.
Don't say yes. Because you just said it. There's only two things that determine time are how far it falls
Yeah. And gravity.
and your gravitational acceleration. The horizontal velocity is not part of the story. And there's no way to put that in there. Dylan,
Yes.
what are the only thing that determines the vertical velocity?
Gravity and mass. Gravity.
And?
Right now, I can.
And the distance.
Yeah. Mass is not a factor. Is Vx a factor in the vertical velocity? No. So there's only two things that determine time and velocity. The gravitational acceleration and how far it falls. That's it. Mass, not a factor. Vx, not a factor. Okay? The fact that this is a top flight golf ball, not a factor. Okay? Only two things. Focus on those. All right. Now, here's what I want you to look at. We're going to look at this ball as it falls through the air. So, if it's in the air for 0.64 seconds, and it's traveling at 4 meters per second, how can I figure out how far it's going to go? Andrew.
You take the time and the horizontal velocity.
Yeah, so I can go, oh, range equals Vx time, right? So I can take that Vx of 4 meters per second. So, who's ever got a calculator, take 4 meters per second times 0.64 seconds.
2.56.
You guys
2 point what?
56.
2.56
56.
Yeah, 2.56.
meters, okay? About 2.5 meters, right? This decent shot, okay? 2.5 meters, okay? Now, if I double the horizontal velocity to 8, Chuck, what's that going to do to my time?
Double it. Wait, the what?
If I double my horizontal velocity, I'm going to launch it at 8 meters per second. What's that going to do to my time?
Nothing.
Absolutely nothing. Why?
Because time isn't affected.
Bingo. Vx is not a factor in that calculation.
There we go, Chuck.
Good one.
How do you know distance?
Now, what's that going to do to the distance, Chuck?
Double it.
That'll double, because then it's going to be going twice as fast, so it's going to go twice as far. Okay. When you deal with projectile motion, you're going to spend a lot of time talking about speed. Okay? So is speed a vector quantity or a scalar quantity?
Vector.
Scalar.
Scalar. Speed's a scalar quantity. It's just a number. So when that thing lands, it actually has two components to its velocity. It has a horizontal velocity of 4 meters per second, and it has a vertical velocity of 6.26 meters per second. So, Sydney, how am I going to calculate the speed of
X squared plus y squared equals this velocity squared.
otherwise known as the Pythagorean theorem, right? So
Okay.
the speed, imagine this. Imagine that you're down here on the ground and you've got like this tiny little radar gun that can measure speed. So what you're measuring is how fast that ball is going right at that point of impact, which is going to be a combination of your Vx and your Vy. Now, if you took that radar gun at that point where it was just launched, what would the radar gun reading be? 4 meters per second, because that's the only velocity that you have, right?
Yeah.
So, as it falls, what happens to your vertical component of your velocity? Thatcher.
Sorry, can you repeat it? Somebody stole my binder. I don't know where it's at.
It's just physics, gang. Come on. We're not talking about binders.
Thatcher.
Yeah.
Thatcher.
I'm sorry.
As it falls, what happens to your vertical velocity?
It increases.
Okay. As it falls, what happens to your acceleration?
It stays constant.
Okay. So, as it falls, if your Vx stays the same and your Vy is getting bigger, what's going to happen to the speed of the ball?
It'll increase.
It'll increase because your vertical component is getting bigger and bigger and bigger and bigger and bigger, right? Okay. So, somebody do the math. Somebody take 4 squared. You already got it?
Yeah, 7.43.
7.43, something like that.
Mr. Hannah, just,
I'm just right. I'm just nice. Like, how did I know that was out of calculus?
I don't know. You're crazy. Crazy.
Imagine if he did that on tests.
Okay. Now,
You know, simple.
we're gonna play the what if game.
I'm good at this.
We're gonna double the height to 4 meters. And we're gonna look at the impact of time, and we're gonna look at the impact on the velocity. So Mr. Hanna, since you seem to be a calculating savant today.
yeah.
If I double the time, if I double the height, am I going to double my time?
Yes,
Yes.
Yeah.
Why?
because what is it? D equals T times V when you double the time, you'll double everything else. You'll double the distance. Right?
Okay,
Am I right?
no,
Oh. Why'd you make it seem like I'm right?
because that's my job.
Wait.
Mr. Hanna,
Like I'm right.
how do you calculate the time? Well, you solve the equation.
I thought you were talking about distance equals time times
Did I
velocity. I didn't know you was talking about the whole Hanna equation.
The vertical distance I'm gonna double,
Yeah, okay,
okay?
yeah.
I'm gonna make it fall twice as far. Will the time double?
No,
Why not?
because
Beyond the fact that I flipped out when you said it would.
your velocity is the same.
No.
So, no.
No. Mr. Hant, how do you calculate time? You solved it.
The Hanna equation, I'm just gonna call it that. I don't want to say the whole thing again.
2x over a?
Yeah.
It's underneath the radical, right?
See, that's where it is. So it's going half.
Half?
Since
So it's gonna, so even though I double the height, bro, it's gonna take half as long.
no, it's gonna say
That's what you said. Oh, it's gonna stay the same. So if I drop it from 2 meters or if I drop it from 4 meters, it's gonna take the same amount of time.
yeah.
Really?
Yeah.
You wanna stay with that answer?
Well, they do every answer to half double. Say what is it?
None of the above.
None of the above.
How?
Do you wanna
math.
take an elegant approach or do you wanna do smash mouth physics?
I'll go elegante.
Smash.
Elegant? Okay.
Fun.
So your original time using the Hanna equation
Yeah.
is 2x over a.
Yeah.
True?
Oh, yes.
True?
Yes.
Now, to calculate the new time, call it t prime, okay? It's still gonna be 2, but instead of x, what am I gonna use?
2x.
2x
Prime time. Okay. I see what you did there.
over a,
Yeah.
right, prime time?
Yeah.
So could I, prime time,
Yeah.
write that as the square root of 2 times 2a, or 2x over a?
Yeah.
Would you just make it up?
Yeah.
So how much is the time gonna increase by?
Like
Root 2.
by
Yes.
whatever the square root of 2 is.
Yeah, gonna increase by the square root of 2, because it's underneath the radical. So that's the elegant approach. You could do the smash mouth physics approach. So let's do the smash mouth physics approach. So I'm gonna take 2 times 4 meters, divide that by 9.8 meters per second squared.
Got it.
What'd you get?
0.98.
9.8?
Yes. Yeah.
90.
Something like that.
0.90
Yeah.
seconds. Now, the original time was 0.64. If the time had doubled, the time would have been
1.28.
1.28.
You see? I'm like a calculator.
But it didn't. Now, out of curiosity, Andrew, take the square root of 2 and multiply that by 0.64.
Same thing.
You get 0.90.
Almost.
Okay?
Almost the same.
Something like that.
So, you can either take the elegant approach or you can do smash mouth physics. I don't care. But here's the question. What's going to take longer to fall? The first 2 meters or the second 2 meters? Deacon,
First two.
why?
Because, well, the acceleration doesn't change, but the velocity increases, and it's getting greater as it falls.
Okay? That's true. But, so, circle back to that idea. On the first 2 meters, what are you starting off at? What's your initial velocity?
0 meters per second.
And then you're gonna go to 6.26,
Yes.
right? So you're going from 0 to 6.26, but on the second half of this, you're starting at 6.26, right? You're still going to accelerate. But you're not gonna take as long, because remember, velocity changes as a linear function of time. It doesn't change as a linear function of distance. Now, Mr. Etheridge, time increased by the square root of 2. V equals the square root of 2AD. If I double the distance, what's going to happen to my velocity when I land?
It's gonna increase by the square root of 2.
Beautiful. Why?
Because you just turn that into a 2D, that gives me 2A times 2D, and then you could just pull out. Like
Beautiful.
the other one.
So then V prime would be 2 times A times 2D, and you would get the square root of 2 times Sydney. If I wanted the velocity to double, if I wanted it to land going twice as fast, what would I have to do with the velocity?
Increase it, times 4.
Or the distance? I'd have to increase by a factor of,
4.
it's the same idea. So if I make the distance go up by a factor of 4, then it would double. Now, the other way that you can look at this is old school V equals V naught plus AT. As it falls, faster, what happens to my acceleration?
Stays constant.
Stays constant. So here's the other way to think this through. If my time increases by the square root of 2, and I'm multiplying that by my acceleration, my velocity is going to increase by the square root of 2. That's the other way that you can view the problem. Cool. Got it? Rand? Okay. Stop that. Let me hand out the lab.